Okay, hello everyone. So let's do today's lead code question. Implement tree prefix tree. Actually, I've already done this question 2 times in December. December was the last time I did it. Okay, so let's do this question. Implement trie prefix tree. So what the question is saying is a trie pronounced as trie or prefix tree is a tree data structure used to efficiently store and retrieve keys in a dataset of strings. There are various applications of this data structure such as autocomplete and spell checker. Uh, so this is a new data structure. It is a tree data structure and it is used to store and retrieve keys in a dataset of strings. We will see how later. And we need to implement the trie class. So trie, this function initializes the trees or trie object, and this function inserts the string into the trie. So we need to insert the string right in the tree, and this function is what does that. Search. This function returns true if string is in the trie and false otherwise, and boolean starts with returns true if there is a previously inserted word that has a prefix. I will explain all this. Okay, so let me explain with this example. So what this means is, first of all, first of all, new trie is created. Okay, so when we call this when we are calling just trie, then it initializes the trie object. So first of all, trie is initialized. So this is a trie class, and this is like a trie constructor. So this will be called, and the tree will be initialized. And whenever we insert apple in the trie, then it will look like a p p l e. And the next time, uh, so when we are searching apple, then it will return true, right? Because there is apple here. So whenever we so suppose we first of all try that insert apple, right? And then if we are inserting, suppose say app I applicate application, then how we'd insert in this try is, first of all we would look if a is there. A is already here, so we do not need to we do not need to create two a separately. It is not like this. So if it was a normal tree, then we might have created like this, right? application, but since this is a prefix tree, so we will see if the prefix is there or not. So the prefix a is there, p is there, p is there, l is there. So we'll only start branch out after I. So it means that the prefix appl, it is the same for apple and application. So lic a ft I O and right. And if there is another word like ap ape, then what would happen? Then it would be like a p, and it would branch out from here, right? So the prefix ap is still we can just use this. And suppose if there is, suppose we are inserting b-a-b-y, baby, then what would happen? Since b is not in the try, right? So we would just start. Suppose we are inserting b-a-p-p-l apple, then we are inserting, suppose we are inserting b-p-p-l. Okay, then since b is not here, b is not the start of any string in this tree, so we need to start b. I mean, so if you see apple and people, the suffix is same, right? ELLP same, but since prefix is different, since the start is different, so we need to store it separately. BP BPP L E. So yeah, so this is how the tree is created. And if we are inserting, suppose CPPLE, then we have to, since C is not either, C is not here, so we need to store C differently. C P P. This is not a prefix, this is not a suffix tree, this is a prefix tree. So we will see if the prefix is matching. Prefix, like we will see if the front characters are matching. If they are not matching, so the front character is C. So if there is no any C, then we would we would make it a new branch. Suppose if there is a suppose we are inserting CPP US, okay, then it would be, then we would first of all look for C. So C is here, then we look for P is also here, then we look for another P is also here, then we look for U. If there was U, then we would look for S, but since there is L, so we would branch out from here. So it would branch out from P. So it would be P's left branch is L and P's another branch would be U, right? I'm just making good better. So yeah, so this is, so how many, if this is a prefix tree, how many strings are there? One is APPLE, another one is APPLIC, and one other one is APE, and another is BPPLE, then CPPLE, and then CPPUS, right? So this is a prefix tree, and this is how we are inserting. So whenever we are searching, then it would return true if string word is in the trie and false otherwise. So if we are searching for apple, suppose if you are searching for apple, then we will see. So if A is there, A is here, P is there, P, another P is here, L is here, and E is also here, right? So it means this is true. Suppose we are just searching for app, then what would it return? What do you think? Is app here or not? Is the word app here or not? So APP, it is here, right? But is this a word, or is this APP, is APP a word, or APP a prefix of some other word? This is not a complete word, right? This is just a prefix of some word. So that is why this would return false, because this is APP is not a complete word. APPLE is a complete word, APPLICATON is a complete word, but APP is not. It is just a prefix, so that's why it will return false. But that is what search is, but boolean starts with. But if we would search for try, starts with app, then this would return, what do you think? What will this return? Then this would return, is there any string that starts with APP? So like I said earlier, APP is not a complete word, but APP is a prefix, right? So that's what we are checking with this. Is APP APP prefix of some word or not? So since APP is prefix of some word, so that is why this will return true. Even if we say that, even if APP, I think even this will also return true, right? Because even if this is a whole word, but it's like it still starts with APPLE. I mean, my name is Soba, and I can say that Soba starts with S. I can say that Soba starts with SH. I can say that Soba starts with SHOB. I can also say that Soba starts with SHOB, right? So that is why I think, yeah, this will still return true. Okay, so that's what all the function is about. So let's see how to implement all of these. First of all, First of all, let's see how to implement insert. So how to implement insert? Um, Good question. How to implement insert? Uh, okay. So there is apple string, and I need to insert it into try. So first of all, like I said earlier, I need to check, right, if the children has a word letter A or not. So it means that this is a root node, and this is a root node, and I need to check this node's children, right? So this is also a children, this is also children, this is also children. So I need to check if its children node consists A or not. So if some of its children consist A, then I should go towards that path. So if this will be current node first, and then if some of the children consist A, then this will be my current node, and I'll check for A children again. So A children has P, this will be my current node, and I'll check if P children consist another P, because I'm searching for apple. I'm inserting apple, sorry. So if there is P, then I would insert P. Suppose if there was no any children after this, then I would insert L at that point. So it means that if there is a node, then so first of all there is a node, and its children's. So there is this all the children's value. So according to this, a node can have many children, right? Can have many children, and children's values are the characters of the string, right? So it means that there will be node children, and node children will be an array, because there might be many children, right? A, B, C. So will node children be array? I mean, because it can be like node children can be array as well, right? It can be node A, node with value A, and node with value B, node with value C, right? And then again, when we are looking at node A, then it might be like node A's children will be equal to P, node with value P, and node P's children again, it will be it will be an array of node P, node with value P. I mean, I can say that this is P1 or P2, so this is different P, and node T. So this can also be, I mean, so children can be in the form of array as well. Is there any other way to store the children value? I was thinking, can I store it instead of array? Because if I am storing this as an array, right? So suppose this has like so this only has 3 children, but suppose this has E, D, E, F, G, S, I. Suppose this has 100 children, then I would have 100 children, and it would be difficult, right? So suppose suppose I was looking for if node's children has node node j as a value. Then if I'm looking for if the children has z as a value, then I would have to look linearly, right? There is no way in an array, because I would have to look if this node has, I'm just using I as a means for traversal. So if this has value j, no. If this has value j, no. If this has value j, no. So I would have to look for all the, so the worst time complexity the worst would be O of n time, O of n for each traversal, where O of n, where n is number of children, right? So this is just for one traversal, but it would be O of h into O of n, right? Because for every level in the height, I would have to do the same. So that is why this is the time complexity. So is there any way to avoid this linear time complexity? I think you can. I think that you have already guessed that we can use hash map, isn't it? So if I use a hash map, like, okay, I can just use this value as a key, right? So A is node A, and B is node B, and C is node C. So if I'm using hash map, then I can just directly Z is equal to node Z. Then I can directly check, isn't it? If the children, then I can directly check if the children has value Z or not. I don't need to go through every single value and check if it has Z or not. I can just directly check if this has my Z or not. That will just take O of 1 time complexity. So the time complexity will decrease to O of h, because I need to do this for every O of, yeah. So this O of n linear time complexity will be eliminated. And space complexity, so the trade-off is space complexity, but that is fine. Yeah, so it means that we instead of keeping node children as node array, we will put node children as a hash map, like A node A, B node B, right? Dot. So what we will do is, first of all, the root node will have, so if we are inserting in a new tree, then root node there will not even be a root node. There will just be a root node with value null. And then so this will be a root node. So when we are initializing a new tree, then we will just create a root node with value null, nothing. And then when we are inserting a new value, suppose apple, then we will start, right? Then we will start. So this will be a node A, and this will be a node, like this will be node P, like this, A, P. We will insert new nodes like that, and this will be value, and the key will be A, P. So yeah, that's how we will store node the children. And yeah, so while inserting, first of all, we will check if, first of all, we will say current node is equal to root node in the beginning, and then we will see if current node, if current node the children, so this will return me hash map, right? So I will say if current node the children has current character or not. So I will look through apple. So if we are inserting apple, then I will look through apple, and then current character, first of all, it will be A, then character will be P. So I'll check if current character is in children or not. If current character is in children, then it means that current node will be equal to, now it will be updated, right? So suppose if we have node A here, then it will return node A, right? So current node will be node A. Now we will look for another one. But suppose if it does not have, then what should we do? We should insert it, right? So if current node has children, then we will insert to current node. So in the beginning, what we can say is, if current node, if this has value, then current node will be equal to, it will be equal to this value. Otherwise what we will do is, otherwise we have to insert right? Current node dot children, or in current node dot children current character will be equal to new node, because we need to insert, right? If it does not have that, then we will insert, how to insert, then we will insert a new node with value current character, or I can just insert a node only. Actually, I don't even need to insert a value, I can just insert a new node. And yeah, so current node the children will be equal to new node, and then I need to update current node, right? Because once I store a new node, okay, so this is a new node, and this new node it is a value, so it will be like, so first of all, node the children will be empty, right? There will nothing, there will be nothing, and I want to insert a, so it will go to this loop, this else block, and I will first of all, I'm doing that current node the children current character a will be equal to new node, right? So I'm just saying that root node's children will be equal to new node. So root node's children will be equal to new node, and yeah, so if I'm going further, then because I'm just using this and in a for loop, so now new node will be the current node, right? So I need to update current node is equal to current node the children current character. I need to update this current, I need to update current node. So I think that what I can do is, if not, so I'm just trying to make this code more cleaner, so I don't need to, because I am doing this here, I'm doing this code and this code outside, so I'll just do this. So if current node does not have, if it does not have a, then if it does not have next character as a prefix, then I will update it and insert new node. Otherwise I will just insert new node, and then in both cases I need to update current node. And then yeah, that's it. Yeah, so suppose if there is, so we did it in case of if there is no node, right? So next is p, right? So I need to, so this will be my current node, and then I'll look if this has a children p or not, because I need to insert p. Since this also does not have any children, because it is just a new node and it does not have any children, so I will insert a p here, and it will be, if it does not have, then it will be p and new node, and then current node will be this. So yeah, and if it had, suppose if it had new node, then it would just not do anything, but it would just update current node and look further. Okay, I think this is it. And even for searching also it is the same, right? I would just keep on searching. So if I'm searching for apple, and suppose if it is, suppose it's just this case only, then it would be, first of all I look for I would start from root node, and then I would see if this root node has a or not. Okay, this has a, and now current node will be this node, and then I will see if this node has children for p or not. Since this does not have it, so I would have written false. And I was talking for searching, but another thing about searching is also that I need also to check if the if the word is a full word, or I mean if this apple is a full word in this tree, or if it's just a prefix. So what I can do is, while inserting only I can check, while inserting only what I can do is, suppose I will be inserting, right, new node a p, new node pp, new node l ppl, and new node pple, right? So what I can do is, while inserting here only I can say that this is false, this is false. I mean, this is not the end of the word, I can say that. So, and this is also not the end of the word, right? Because it is just p. While inserting only, I can say that this is also not the end of the word. So only when I come to the last character, I can say that this is the end of the word, true. So I'll also store this information. I will show you how I will insert this information, but just know that I'll also insert this information if this is just a word or it is a prefix. So if I am searching for, if I'm searching for apple, then I can see that, okay, apple, okay, this is true, so I'll return true. But if I'm searching just for app, then I will go just until app, and I can see that this flag, this, this is false. So it means that it is just a prefix, not a whole word. So I return false, true for that. And if I'm searching for starts with, then I don't even need to check for this value, I'll just return true. If I come until, if this tree has app, then I would return true. I will not check for this value. Okay. Okay, I think if you are not clear, then you might be clear after I start writing code. So let's start writing code then. This is the main. I'll just put all of these above so that I don't I can see this code directly. So first of all, let me start initialize a try. So while initializing a try, like we said, we need what do we need? While initializing try, we need a root node, right? So this dot root is equal to new. We need a node. So is there a node here anywhere? I think that we need to build a class then node. So no, what will node have? Node will have this dot, this the children. Node will have this dot children, and node will also have this dot each word is equal to, it will be false in the beginning. So I'm just writing it. So this dot children, you understood this, right? So all the node has children, and each word is for this value false. So initially it will be false, and this dot node, this dot root will be new node. So this will be a node. I think yeah, this might work. This will be a new node, and this is a new class, and this is a node, new node. I think I just need this only. So whenever someone initializes new try, then the root will be initialized, right? The root will be initialized with children empty and each word false. And now if I want to insert, then like I said here, I need to I will say that current node is equal to root node first. So current node will be equal to this dot root, and I need to check this, right? So I will loop through the word. So if the word is apple, then it will be for const ch of word. So this will be, first of all, a will be inserted, right? So first of all, a will look for if current node has a or not. So if current node, I can just say this, right? If current node does not have children, if current node does not have children ch, if it does not have children ch, then I need to insert it, right? So I will current node the children ch, I will add it to the hashmap. So this will be my key, and my value will be a node. So it will be a new node, and then this will be current node will be equal to current node. So now my current node is updated, right? Now my current node is updated to node A. Now I will need to insert P as well. So P will also be inserted in the same way. So since this new node will not have any children with P, so it will insert for this new node also, so this is a new node, and for this new node also, this new node's children will be equal to a new node which is it will be equal to, a hash map with p key and a new node value. So yeah, at last, after we finish complete inserting pple, what we will do is we will insert current node dot each word equal to true, right? So first of all, we will insert this node, this node, this node, this node, and the current node will be at the end of the loop. The current node will be equal to this node, and now we know that this loop has exited. It means that the last node will be equal to the the last characters node. So we will just say that this is the end of this word. So we will raise this flag true, so that when we are searching for apple, then we know that okay, this is true. And this is how we will insert. And actually searching is also similar. So when we are searching also, we'll search the same way, right? First of all, we'll look at the root node, and this will be the current node, and we'll see if current node does not have children, then in case of sorting, so this is for inserting. And even in case for sorting also, so we'll say that if current node does not have children, then we will just return false immediately, right? Because suppose if we have appler, then since e does not have a children r, so it means that there is no there's not, I mean, if I was looking for a word appler, then I came up to e, but since e does not have a children r, so it means that there is no appler in this tree, so I will return false immediately. So that is what I will do here. So this is a similar code here, but I will just return false here immediately. And then at last, yeah, I will just return false immediately. And at last, so suppose if I'm checking for apple and I came up to the so since it is not written, we did not return false, right? So it means that if I exit this for loop, it means that I came up to e. So it means that the tree has the character a p p l e, but I need to check if this is the end of the word or not, right? So I need to check if current node current node is what is equal true or not. If it is true, then I will return true, otherwise false. So I can just say that I can just return this. So if it is true, then it will return true. But suppose if it is just app, if we are just searching for app, then this loop will then it will come until this line, right? It will not return false immediately, but it will come to up to this line. But we know that each word is false at this node. So I mean, yeah, so we know that app is not is false at this node, right? So it will return false. Okay, so this is search. And for actually for starts with, we don't even need, we can just return true immediately. We don't even need to check for, it is the same as search, but we don't even need to check if it is false or true. So even if we get up to this point app, we know that there is app in this tree, so we'll just return true. We don't even need to check if it is false or true, because we are not checking if that is a whole world or not. Okay, I think this is it. So I wrote everything. Let me check if there is a typo or any conceptual mistake. So I'll go through my code at last. Node function children, it is a hash map, and this dot is word is equal to false. That's fine. This word is equal to new node. New node, I started a new node, new class here, and whenever someone calls this class, it will instantiate this dot root, and node dot children, and current node will be this dot root, and ch of 4 children ch is equal to new node, and this will be a current node, the children h, it's written true. Oh, is word is equal to true, and then return its word, ch of word, the children ch written false, the children ch, current root is equal to this third root, C as a for. I think this would work. Oh no, what happened? What is not defined? Oh, this is prefix. Okay, will this work now? Wow, great, great. I hope that you guys understood my explanation. uh yeah, bye everyone, thank you for watching.